Thanks so much for having me here. So the story I want to tell you starts out with a classification problem. So what do we want to classify? I'm looking at symplectic fillings of Seifert fibered spaces over the two-sphere with a canonical contact structure. So what are all of these things? So symplectic fillings. Sometimes these are called strong symplectic fillings. In my case, all sorts of symplectic fillings will turn out to be the same. But I'm thinking of a four-manifold. So you can think about any even-dimensional symplectic manifold, but within this talk, there'll be dimension 4. And it has a non-degenerate closed 2 form on it. And it has boundary, which has a nice compatibility with the symplectic structure, namely the boundary is convex. So essentially that means that for your manifold, you always have a nice smooth colored structure near the boundary that looks like the boundary across an interval. And now we want the symplectic form to be compatible with this product structure. So what that means is that on each level set, you have the symplectic form is encoded by a contact structure. So you can get a contact structure by taking this product direction, which gives you a vector field. And if you have this condition on that vector field that it's a Liouville vector field, that's telling you that your symplectic form essentially looks the same on each level, and it's encoded by the kernel of the one form gotten by contracting in this I direction, and then restricting it to the level set. And that's a contact structure. And then the convexity condition says that because our symplectic form should be non-degenerate, we need it to either be expanding or contracting as we go out towards the boundary. And so convex means it's expanding. So omega is expanding out towards the boundary. So we're looking at these types of symplectic manifolds with nice boundary. And I'm going to fix the type of 3-manifold that shows up on the boundary. So M is going to be this Seifert fibered space. So as a 4-manifold topologist, I'm going to think about these Seifert fibered spaces, which are 3-manifolds, as coming from the boundary of a particularly nice 4-manifold. So it will be the boundary of a plumbing of disk bundles over spheres. And the plumbing should be plumbed together according to a star-shaped graph. So there's going to be, this graph will have one central vertex of valence k, and then k arms emanating from it, which are just linear. So this has k arms. And then the plumbing is determined by this graph if you put weights on it. So you have some integer weights on each of these vertices. And each vertex is supposed to represent a disk bundle over the 2-sphere. And the weight tells you its Euler number. So you can basically think about this as finding an embedded 2-sphere inside of a 4-manifold whose self-intersection number is given by that weight. And then the edges tell you how to plumb the disk bundles together. And so if you're thinking about finding a configuration of spheres inside of a 4-manifold, the edges correspond to positive transverse intersections of those spheres. So vertices are spheres, and edges are positive transverse intersections. And then if you find such a configuration of spheres inside of a four-manifold, small neighborhoods of the union of those spheres give you this four-manifold plumbing. And the boundary of that is a Seifert fibered space over S2. So any Seifert fibered space over S2 arises as the boundary of such a plumbing. And you get a little bit of repetition if you allow yourself to vary all of these integers and the number of arms, the number of weights, or number of vertices in each arm. So to normalize this so that we only get each oriented three-manifold exactly once, you make an assumption that the weights in the arms are at most -2. And then each of these four manifolds corresponds to a unique Seifert fibered space, as long as you allow the weight on this central vertex to vary through all integers. So for my purposes, I'm going to put a restriction on which Seifert fibered spaces I'm looking at by just putting an inequality on that central vertex. And part of this restriction is motivated by making the classification of fillings simpler, but you would need at least something to get a canonical contact structure on the boundary. So where is this contact structure coming from? Well, this four-manifold plumbing has a particularly nice symplectic structure, which has convex boundary. So by then contracting the Liouville vector field into the symplectic form, the symplectic structure tells you a contact structure on the boundary. And so that's how you figure out what this contact structure we're looking at is. And so one other sort of nice thing about this symplectic structure, it's like very concretely constructed by constructing a symplectic structure on each of these disk bundles. And so the core spheres, the zero sections of each of these bundles, are symplectic submanifolds of this four manifold with this particular symplectic structure. So this contact structure on the boundary is not canonical in the sense that it's the unique contact structure. It's not even the unique tight contact structure or the unique fillable contact structure. But this is sort of the terminology used in the literature, partly because this is the contactomorphic to the contact structure that arises when you view these spaces as the link of an isolated normal surface singularity. So in that case, you're looking at a singular four-manifold with this boundary, but it has a complex structure on it. And so when you cut off a neighborhood of that singularity, you can use the complex structure to define a contact structure. Oh, yeah. So in order to get this symplectic structure on the plumbing, you need the graph to be negative definite. And I think that's probably enough to define it as a normal surface singularity as well. And so this is a little bit stronger than what you would need to get a negative definite graph. So I'm assuming slightly more than what we need to define this contact structure. All right, so is it sort of clear what the problem is? Okay. Yeah, so maybe it's worth having like a particular example throughout time. So any example is just specified by a graph. And so let me maybe keep this particular graph around. So then if you want to understand, say, a surgery diagram for your Seifert fibered space, you just have a surgery curve for each of the vertices in here, which glues together with the core of the, well, if you're thinking about this as a handle body diagram, the core of the two handle glues together with the Seifert surface to give you a sphere. of the right self-intersection number, and then that induces the surgery diagram on the boundary. The contact structures can be described explicitly in terms of open book decompositions. So this existence of a symplectic structure on the plumbing for negative definite plumbings is a result of Gay and Stipschitz. And it was strengthened by Gay and Mark to actually have a Lefschetz vibration supporting this symplectic structure. And it's a really explicit Lefschetz vibration. So, and then you get an induced open book on the boundary. So you just sort of put in a sphere for each of these vertices, and you glue them together along the plumbings, and then you put in some holes depending on the self-intersection numbers. So this is sort of the generic fiber of a Lefschetz vibration. So these are boundary components, 4 boundary components. And then the vanishing cycles, there's one along each hole and one along each plumbing piece. Oh, there's another hole up here. So, if you sort of tell me what perspective you want to view these from, then maybe I can. Name the topological space.
Yeah, just give me a 3-manifold.
Any of the simple singularities.
Yeah.
The Deacon diagram that describes the.
Or any Brieskorn sphere. So not all the Brieskorn spheres are going to have this condition, but and the simple singularities will also, to some extent, have that issue. You could think about lens spaces as like star-shaped graphs with one arm. So in that case, you get a lens space, and this is sort of the next natural generalization of a lens space.
So what is it for like a simple lens space? What is the graph?
It's going to be linear. So if you have any weights on here which are negative, less than -1, then you will get the boundary as a lens space. And the lens space itself, the P and the Q, are determined by the continued fraction expansion here. And so in general, with the Seifert fibered spaces, they're determined by a couple of invariants. One is this central vertex, and then for each of these arms, you look at the continued fraction expansion, and that gives you a fraction which tells you sort of what the singularities in the Seifert fibered space look like. Each arm corresponds to a singularity.
So excuse me, you plumb some 2-disk bundles. Which kind of bundles?
Yeah.
One structure on this, what kind of symplectic structure do you have?
So on these bundles, you're going to have the section direction is symplectic and the fiber direction is symplectic. And then there's just a little bit of tricky stuff to actually do the plumbing. And that's modeled on like a toric geometry model.
You do not allow the coordination bundles.
Right, because that's kind of Lagrangian.
Yeah, I can perturb the
Yeah, and they should be deformation equivalent, I think. Okay, good. All right, so let me state what sorts of results I can get for these fillings. All right, so let's make this a theorem. So once we make this assumption about restricting to something like half of all the Seifert fibered spaces, K is a natural number. Mm-hmm. It's the number of singular fibers. So then I'm going to add in the qualifier that these fillings be minimal, so they're not blow-ups of anything. You can always symplectically blow up a symplectic filling to get a new one, but it's not a terrifically interesting change, and so we're going to stick to just understanding the minimal ones, then first of all, these fillings are going to realize finitely many values of Euler characteristic and signature. So their homological invariants are restricted into some sort of finite range. And if I make some stronger assumptions about the Seifert fibered space I'm looking at, so under stronger hypotheses, which either means that I'm looking at a small number of singular fibers, or I put some additional negativity condition on this central vertex weight, then there are finitely many diffeomorphism types of these fillings. And so these finiteness results are sort of the easiest things to say, but they're not really the strongest things that I can say about these symplectic fillings. So what I really mean by there are finitely many is there is an algorithmic combinatorial process for producing a list of possibilities for either just the homological invariants, or in these stronger conditions, you can produce information which tells you what sort of diffeomorphism types these fillings could have. And so really the best thing you could ask for in a classification result is to actually list out all of the diffeomorphism types, or maybe up to symplectic deformation. And that's sort of a refinement that I haven't quite achieved yet. But at least for the diffeomorphism types, in these stronger cases, if you give me any Seifert fibered space that has like a small number of singular fibers or has this negativity condition, I can, after some amount of time, draw out a list of all the diffeomorphism types. So I can give you a handle body diagram, and I can give you a Lefschetz fibration for that filling. So at least for many infinite classes, I have explicit descriptions of these manifolds. So that's encoded in a Lefschetz fibration for all the fillings of the Seifert fibered spaces in that class. Yeah?
Do we have example or one diffeomorphism type but two symplectic structures?
That's a very interesting question. So in yeah, so for now, I think the answer is that I don't know. But in at least some of these cases, I can say that for each diffeomorphism type, there's only one symplectic deformation class. Yeah.
So your examples are Stein?
Yes. So one thing about these particular Seifert fibered spaces and these contact structures is that they're in fact all supported by planar open books. So Wendel's theorem says that in the planar case, Stein and strong symplectic and weak are all the same. Yeah. All right. So I want to tell you something about the proof, partly because it's the proof contains some of the computational information of what you would actually do if you wanted to figure out this sort of classification. So the proof idea is in some ways a generalization of what McDuff originally did for lens spaces LP1, and then Liska later did for general LPQ lens spaces with a canonical contact structure. So basically the one-armed case was done in the past, and now I'm finding these generalizations to Seifert fiber spaces. And a number of new complications show up in this more general case. But the idea is that we're trying to identify what the symplectic filling could be. And all that we know is what it looks like along the boundary. And so using the information of what the symplectic structure and the manifold looks like on the boundary, we can choose a particular piece of the manifold or a particular concave cap to make this a closed manifold. So the Seifert fiber space that you choose determines a concave cap. So, if I give you this particular graph, then I use the data of this graph to construct, in fact, another plumbing. So this is actually also a plumbing. But instead of the negative definite plumbings that I had as these convex fillings, so maybe one thing I didn't mention is that I'm always starting out knowing one of the fillings, which is the plumbing. And I want to understand what are other possibilities. So there's sort of a nice construction of Stipschitz-Sabo and Wall, which takes this negative definite graph and basically flips it over and renormalizes it so that you get plumbing which has concave boundary. And so in this particular case, you do some construction and you find out that the boundary of this plumbing is the same as the boundary of this plumbing except with reversed orientation. And so there's also a nice symplectic structure on this particular plumbing, except instead of the symplectic form expanding out towards the boundary, it's contracting. So these two pieces, they glue together and they give you a closed symplectic manifold. And now we want to know what this piece is. So there's a theorem of McDuff which identifies what this closed symplectic manifold is. So if you have x omega closed symplectic, and it contains a symplectic two-sphere of positive or non-negative square, in our case, it's going to be this +1 sphere. So let's call that embedded two-sphere that's symplectic C. Then this triple xc omega is symplectomorphic to a blow-up of CP2. That's the 4 manifold. The two-sphere gets identified with the complex projective line, and there's a standard symplectic form on CP2. And so really the only choice you have is in the weights of the blow-up. So now we know what the whole symplectic manifold is, and we know what the top piece is, and we're trying to identify the bottom piece, what it could possibly be. So the only tricky thing is that that's sort of what gives you interesting things. So you know that you're trying to send this +1 sphere to the CP1, and then the question is, how can you embed these other spheres? And so we sort of reduce the problem to classifying embeddings of this concave cap, which is a plumbing, into blow-ups of CP2. So this is the new problem that we're trying to solve, is classifying these embeddings. And we know at least a number of things that these embeddings should satisfy. First of all, they should be symplectic. And in the symplectic structure on this concave cap, all of the core spheres here are symplectic submanifolds, and the +1 sphere is sent to CP1. So that gives us a lot of information to work with, but it doesn't completely determine everything. So let's say if we want to understand where this plumbing goes to, it basically suffices to understand how you can embed the core spheres into CP2 blown up some number of times. And so to understand this sort of embedding, it simplifies things a lot if you blow down into just CP2, and then you want to see what do these spheres descend to down here. So there are a number of ways which make this blowing down process a lot more controlled. So you're going to choose an almost complex structure, J, which is tamed by your symplectic form. And these symplectic spheres are symplectically embedded. And additionally, they're omega orthogonal to each other. So you can choose your J so that they're all J holomorphic. So the embedded spheres are J holomorphic. And then McDuff tells you basically that you can blow down J holomorphic exceptional spheres and so all of the spheres in the picture are J holomorphic. So because you have positivity of intersections for J holomorphic spheres, the algebraic intersection data is determining the geometric intersections. So as you blow down, you just have to figure out the algebraic homological data to understand what's going on, how those blowdowns are affecting these spheres. So what it turns out in the end is that so this CP1 is algebraically disjoint from the exceptional spheres, so it's really unchanged by all of these blowdowns. You do some homological analysis, and you find that if there were sort of more spheres in this concave cap, which you're trying to embed, that were not adjacent to this central +1 sphere, they would disappear under blowing down. So you'd blow down, take the proper transform. Eventually, they would become -1 spheres representing an exceptional class, and you'd blow them down, and they'd disappear. So what you get is the K spheres, which are intersecting that +1 sphere, they remain under blowing down, and they represent the same homology class of the complex projective line. So you have some algebraic +1 intersections, and because they're all J holomorphic, each of them intersects the other in a single point. But the sort of interesting information that shows up is how these intersections occur combinatorially. So originally, there were these 4 -2 spheres intersected the +1 sphere in 4 different points. And now as you blow down, they start to intersect each other. And every pair has to intersect exactly once. But it could be that 3 of them all intersect at the same point, and then you still have the same pairwise intersections. But the embedding and the complement of the embedding look different depending on this combinatorial data. So there's this combinatorial data about the intersection pattern. So maybe you have a triple point and then 3 double points amongst these 4 spheres in the arms. And there's information about how do you blow back up, and those are sort of related to each other. So if these three spheres are all intersecting at a single point, that means that you took one exceptional sphere up here that sort of intersected all of these, and when you blew it down, they all start intersecting in a single point. And so how to blow back up, and this combinatorial data, this is all determined by the homological information of the embedding. So what I mean by that is for each embedding, there's going to be an induced map on H2. The second homology of this plumbing is just generated by each of these spheres. And the second homology for blowups of CP2 have a standard basis. And so what you want to understand is what could these spheres be sent to in terms of the standard basis over here. And you have the adjunction formula putting some restrictions on. You have like the intersection data of these spheres. These two have to be algebraically intersect 0 over here in this embedding. And so all of that information makes the possibilities for this homological embedding finite combinatorial problem to classify. So the final piece of information to really understand how these embeddings are classified is to classify the piece down here up to isotopy. So we want to classify these embeddings up to isotopy. And by isotopy, I mean if there's a triple point of intersection, that should be held onto throughout the isotopy. Because what I really care about is being able to blow this back up and look at the complement. So I don't want the complement to change during the isotopy. You can also think about maybe you're isotoping a small regular neighborhood of these spheres embedded into CP2. Yeah. So this is it would be lovely if I could make this isotopy some kind of symplectic deformation throughout. But so in this case, what I show is that there's actually a unique smooth isotopy class under these stronger conditions. And the idea is I am holding on to 2 points on each of these lines and isotoping them to, so these right now are just J-holomorphic lines. And I'm going to isotope them to genuine complex projective lines. And then in these simple enough scenarios, the structure of the complex projective lines in those configurations have unique embeddings up to PGL2C diffeomorphisms. So how do I get the isotopy to complex projective lines? I'm relying on Gromov, which says for each J, there's one of these J-holomorphic curves through any 2 points. So I can hold on to 2 points at a time and then vary my J towards the standard complex J. And so that starts isotoping each of these spheres, and it fixes whichever points on the sphere I'm holding on to. And so the additional conditions to get this diffeomorphism classification are either to say there are a small number of lines down here, or there's a small number of multi-intersection points. So I can add like 25 extra lines through here, and it's not any harder to do the isotopy. Yeah, I can add 25 billion lines through there if you want. So that having a small number of intersection points with a lot of lines coming through is forced by this other negativity condition. So that's where those are coming from. So there's a unique isotopy class under these stronger conditions. Then for each isotopy class, or for each homological embedding, I know that there's a unique smooth embedding into here, and then I just cut out that smooth embedding and look at the complement, and that's the diffeomorphism type of my filling. So once I've solved this problem at the homological level, in these particular cases, I've solved the whole problem. All right. So that's sort of the summary of the proof. So
maybe you said I missed it. Is the easier or less minus k minus 1 assumption?
Oh.
When you do the transform, you get to plus 1.
Yeah, sorry, I forgot to say that. So that's exactly right. So being able to get a concave cap with a positive sphere here relies on E naught being at most minus k minus 1. I could get a 0 here if I let it be minus k. There's still a classification theorem of what the whole manifold is, but it's not uniquely classified. Like that sphere represents a fiber in any fibration over a surface. And then things just get much more complicated. But there have been a couple of examples that were worked out by Stephen Schoenberg in his thesis, in a later paper. And he did like way more work for just like a couple of examples. So if you had a particular configuration that was like really awesome that you really wanted to understand its fillings of, then maybe it would be worth it. But for the general case, I'm putting this slightly stronger restriction on. All right. So the next thing that I want to do is say what I can actually do with these fillings. So once I solve this homological combinatorial problem, I get this data about these embeddings. And in a lot of cases, you can just realize those embeddings by looking at a configuration of genuine complex projective lines and blowing up, and then looking at the complement. And then you have this picture of a filling, and often it's not too hard to make that look like a Lefschetz vibration. So we get these new examples of fillings, and in particular, the plumbing filling is frequently not the only one. There are lots of others. So what can we do with these new examples of fillings? So what I did, which is joint work with Chara Karakurt, is we tried to build some interesting four manifolds. So interesting here, I guess, means symplectic four manifolds with exotic smooth structures. And these are closed. So closed symplectic four manifolds. So the idea was that we have this nice plumbing filling, and what Gay and Stipchitz showed is that if you find any configuration of symplectic spheres inside of your symplectic four manifold, which intersect according to this graph, then you can find arbitrarily small convex neighborhoods of those spheres which support this contact structure that we're interested in. And so if you find this kind of embedded inside some nice closed four manifold that you understand, then what you can do is cut out the plumbing, so cut out a neighborhood of these symplectic spheres, and glue in any other symplectic filling. So this particular example, I can fully classify the fillings, and in addition to the plumbing, there are two others, up to some isomorphisms. One of them is gotten, if you're familiar with rational blowdown, by rationally blowing down the -5, -2. And the other is so there's, in this case, there is some filling which I have a maybe explicit Lefschetz vibration for, and the filling has Euler characteristic 3. So it's close to simply connected. Its pi 1 is Z mod 2. It has 2 generators of second homology. It's negative definite. In fact, all of these fillings are going to be negative definite. That's sort of a corollary of McDuff's theorem and the existence of these concave caps. So we're replacing this with something which is smaller. It has smaller B2 minus. So we're referring to this process as star surgery. We're cutting out some star-shaped configuration of spheres and gluing in something else. So what sorts of things can we construct using this? So what we could show is there are lots of ways to construct symplectic 4 manifolds using star surgery, which are homeomorphic but not diffeomorphic, so they're exotic copies of various blowups of CP2. So we can do CP2 blown up 8 times, 7 times, 6 times. And we can do each of these in a number of different ways. So what are the manifolds that we're starting with? We're doing this, we're finding these embedded spheres in, a blow-up of an elliptic surface, E1. So we have this elliptic fibration, which has most of its fibers look like tori, but they degenerate at certain places, and you get things like maybe a necklace of spheres. And so these types of spheres, the elliptic fibration has some actual complex structure on it, and so looking at a compatible symplectic form, these spheres are going to be symplectic spheres. And so this is approximately where we're finding these embedded spheres. And so once we find a configuration like this, we can just swap it out for our alternate plumbing. And everything is really explicit. We have like a handle body diagram for this filling, so we can compute what happens to the fundamental group when we glue these 2 pieces together. It's just basic algebraic topology, Seifert-Van Kampen theorem, and we know what the Euler characteristic and signature of the resulting manifolds are. And so understanding the homeomorphism type of the resulting manifold is simple enough. And then to distinguish the diffeomorphism types from the standard blowups of CP2, we compute the small perturbation Seiberg-Witten invariance. So there's a lot of computations to do, but we get a lot of examples. So historically, there was a lot of interest in finding exotic copies of manifolds with small Euler characteristic and in dimension 4. And so there was some greater difficulty in applying constructions to create such examples, but there was really a big wave of efforts made towards this goal. And so manifolds which exhibit the same types of smooth properties as our examples have been constructed before in the literature. And one of the main tools that has been used to construct these is the rational blowdown of Fintelschel and Stern, or generalizations by Park or Stipchitz, Szabo, and Wall. And the star surgery is really motivated by the rational blowdown, and it's viewed as a generalization. So the rational blowdown is looking, at least for Fintelschel and Stern's original rational blowdown, we're looking at a particular family of linear Plumbings. So you can view this as a special case of a star-shaped Plumbing. And it replaces this with some other manifold, which is a rational homology ball. So if you find these embedded spheres inside of your 4 manifold and replace them with this rational homology ball, you're killing off all of the generators, the rank of the homology generated by each of these spheres. So you're reducing the homology by a lot, and that's part of why this operation is so effective for finding small exotic 4 manifolds. So the idea of star surgery is that we're really broadening the class of configurations of spheres that you can look at and try to replace symplectically, which somehow the symplectic structure and the Seiberg-Witten invariants are so closely intertwined that looking at symplectic operations is sort of a good thing if you're trying to look for exotic smooth structures. So we're saying, instead of just looking at these classes of spheres which can be replaced by a rational homology ball, which has sort of the smallest Euler characteristic possible, let's just take whatever we're given, what sorts of spheres we find, and see what we can replace it with symplectically. So we're looking at different embedding, a larger class of embeddings, but we're not killing off quite as much of the homology in the star surgery process. So a question was raised when we first started thinking about this, which is related to some results about lens spaces. So if you consider the corresponding star surgery for any linear Plumbing, so it could be any negative weights here. The boundary of this linear Plumbing is a lens space, and the symplectic fillings of lens spaces with this canonical contact structure were classified by Liska. And then more recently, Bhupal and Ozbachi showed that, in fact, all of those fillings that Liska gave us are obtained from the original Plumbing by doing a sequence of rational blowdowns. The Fintelschel and Stern family, and then sort of the generalization by Park. So here there's one integer parameter. Park has some other family of linear Plumbings which has 2 integer parameters. So if you try and look at star surgery for just this linear case, then you're not getting something much more general than rational blowdowns. You're getting sequences of rational blowdowns. But so a question was brought up, is star surgery more general than sequences of rational blowdowns? And it's not terrifically surprising that, that the answer is yes, it is more general, because we're looking at many more configurations. But it's really a pain to show that particular operation is not equivalent to any sequence of something. So right now, what I can say is there exists one star surgery, which cannot be obtained by any sequence of rational blowdowns. In whatever most general sense you can think of for rational blowdowns. So you can't just find, symplectic. Not the most general, but if you're doing this within the symplectic category, then there's a Plumbing which can be replaced by some filling of Euler characteristic 2, and there's no way to get from here to here by doing any sequence of rational blow-ups, blow-downs, anything like that. So that's sort of some evidence to say that maybe this star surgery could be used to produce some new phenomena in four-manifold topology. So right now, what Char and I have shown is that there are really a lot of ways to use these operations to construct smooth phenomena that four-manifold topologists are somewhat familiar with at this point. And it's unclear whether the manifolds we're constructing are diffeomorphic to other examples in the literature. They all share the same Seiberg-Witten invariance. So it's kind of rough to try and compare them, though I have some thoughts on that. But I think that we have a long ways to go in terms of utilizing these operations to their fullest potential. There's sort of two sides of the problem. One is, what configurations of spheres should we be looking for embedded inside of four manifolds? So that's really understanding the classification of fillings problem. When can you find interesting and small fillings? And then the other side is finding good four manifolds where we find these embedded spheres in these configurations. And so far, we've been working with just these elliptic fibrations, which are somewhat standard examples to look at in the literature. And we're constructing all kinds of different types of singularities because we really need to understand the homology classes that are represented by each of the components in the singularities. And so we're blowing up lots of Lefschetz fibrations, but I think there's really a lot more general things that could be done. So there's still plenty of interesting stuff to do on the four manifold side, and additionally plenty of work to be done in generalizing the filling classification as well. So this is just the beginning, but I think that's all I have to say.